addressing covert termination concurrent information flow systems, and Deian is giving the talk.
Can you guys hear me? All right. So this is joint work with Alejandro Russo, Pablo Brias, Amit Levy, John Mitchell, and David Maziris. Actually, most of these guys are here, so feel free to bother them as well. This talk is about an concurrent information flow control system called LIO, and I gave, I guess, the sequential version of this talk at the last Haskell Symposium. And I'd like to set up kind of the picture that we're trying to create with information flow control, and specifically with LIO. And the scenario where we envision using LIO and this library language level approach is a web framework. And this web framework is actually quite different from, say, Rails or even from Yesod, in that most of the website is built from completely untrusted applications, or apps, if you want to think of the app model. So one example might be, say, a messenger application, which lets you exchange messages with users, maybe a photo editing application, or like something to send mail-like things. Now, since these applications are all built by third parties, maybe users as themselves, and they're operating on user data, we'd actually like to make sure that when we actually run these applications, it doesn't violate your privacy. So we can take, say, the Facebook approach and use access control lists. So we're going to, say, have a messenger application always ask you, are you willing to let this application look at your data? And once you click yes, this application can look at your data, but once it's doing that, you have no guarantee as to what this application can do with your data. So maybe a part of the implementation would have, say, a function like send message. And this send message takes the user you want to send this message to and the message itself. And in the process of doing this, so let's say Joe here is invoking this application, this function. The application now looks up Bob's inbox and takes all his current messages, and now all he simply does is concatenate the new message to the old message list, and finally writes it back to Bob's inbox. So this is a nice, very simple implementation, but at least with the current design, you can have something like this. So what this current application can do is check if Bob has ever actually spoken to Julian Assange, and if that's the case, alert TSA. So this would look something like this. If the app, maybe it's malicious, maybe it's not, it's leaking information in some other ways, a TSA agent would now just always send Bob a message. And when it sends a message, the application can scan all the previous messages. If he happened to send Julian a message, it would leak to the TSA, and at the same time pretend like it's doing its real job. So that's, to some degree, the worst part about it, in that these applications can be doing malicious things and you'll never actually know about it until you reach the borders. So the question is, what is the actual problem? Should we just not allow this application to access your data? Or should we just prevent it from talking to the TSA? The answer is no, we should allow it to do both, just not one after the other. So in other words, the more general thing we want to do is limit who an application can talk to once it's read sensitive data. And this is exactly what information flow control does. So in information flow control in our system LIO, what we do is label data such as your messages, your file handles, and so forth with a security level or a micro policy. And what this policy does is it just specifies who can read this piece of data. So in this case, I'm using, say, a 4-point lattice. At the bottom of the lattice, we have this white box, which just denotes public data. So this public data can be read by anybody, and so it flows up. And now we have two different users. So we have Bob, who we denote by this red box. And you can see public information can be read by Bob because it flows up. And we have, say, the TSA agent who's in blue. Now the important thing to note is that there is no line connecting the two of them. So there's no information flowing from Bob to the agent or the other way around. But maybe there's a computation that performs something interesting with Bob's data, but it also uses some TSA information, and the label of this computation should at the end of the day be a combination of the two. Now in the system, this means that neither Bob nor the agent will be able to see it, but maybe in some other world they can both agree to be classified as a piece of data. Okay, so with that in mind, that we can label, say, messages and so forth, the way we enforce information flow control at the computation level is by using a new monad called LIO. Now this monad is opaque, and all it simply does is it keeps track of a current label. This label is in a sense of taint on what the application has read. So if you've read some sensitive information, this will be reflected in the state. And because this records what you've done so far, what we can do is, from now on, restrict you from like talking to, say, the TSA. So let's go back to the previous example where we have the messenger application being used to send data. So on the left we have a message that's labeled public, so it's simply forwarded, invoked, it's just invoking the application. Now this application will bind it locally and it will read Bob's mailbox. The messages from Bob's mailbox, they're all labeled with red. They're read by the application, and what we're doing now is we're taking the application to reflect that it's read something sensitive. So once it's done this, we can now still write it to Bob's mailbox back because we have the red flowing to the red. That's completely fine. But suppose we have the previous example of send message that's actually malicious, and on the right side we also have the TSA. And once you've read this piece of information, so you are tainted, now you'd like to actually send this to the TSA. And what LIO does is when you reach this point, it asks the question, can this information flow to the TSA? So since the current label of the application is red, and we never had a connection between red and blue, this will be disallowed. In LIO, what actually happens is you get an exception, and in our model, essentially the program terminates. So we've prevented a leak to the TSA, but we've introduced a slight problem. So because we're disallowing that kind of leak, also you can imagine extending the application where you want to just say broadcast the same message to different users. So maybe you want to send this message to Bob, but you also want to send it to John. It's the same message. Well, LIO, after having read Bob's message, now reads Bob's inbox. It gets all its messages, and now it wants to just append that back to John's message inbox. But it actually can't do this either, right? Once it's been tainted, the new computation will have both Bob and John, and since that doesn't flow to the yellow box, LIO has effectively prevented a program that's potentially useful and not actually leaking information from running. So how do we address this problem? Well, the strongman solution is to just use this function we call discard. So what discard does is it lets you execute a potentially sensitive computation, and instead of letting you look at the result, and doing that, raising a kernel label, what it's going to do is just it's going to execute this, not show you the result, but keep your current taint the same. So if we take the send message example, now we're going to wrap all these send messages with discard. So basically, if we start with a completely untainted application that's ready with messages, now we're going to create a discard block. So discard block starts also in a completely untainted state, and locally bind a message. It's going to read Bob's messages. It's actually going to be tainted, but note that the actual application itself is not tainted. It's just this like inner sub-computation. And finally, this inner computation can write back to Bob's inbox. So we've reached the state where we're at the second point of the loop, and now we can actually read John's messages and write the new message to his inbox. So we can kind of still prevent the leak to the TSA, but also perform the more interesting computation. So I said before that there's no actual leak because we don't show you the result, but that was a slight lie in that you can leak information, but the way you do it is using the covert channel. So the actual leak itself is in not terminating. So this card doesn't prevent such leaks. So here's a concrete example of what the evil send message might do. So it will create this card block, and within this block it will do what it's done before. So it's going to read Bob's messages, and it's going to search all these messages to see if Julian has ever been a recipient. If that's the case, it's not going to terminate. Outside of this discard block, we're just going to write to a public channel, basically clean. So an attacker, the TSA agent observing this public channel, recall that the thing, because we have this card, we're not tainted, you can actually perform the write to the public channel. So if you just look at the public channel output, if you see clean, then you know that this corresponder has never spoken to Julian. On the other hand, if you don't see anything on the channel, there's a thread looping forever, and there's a good chance that you'll be detained at the next thread. So this is the termination attack, and it leaks effectively 1 bit. And you can say we can address this at the web framework level or a different higher level abstraction. Or we can just say, let's just use a different attacker model and prove something like termination insensitive non-interference. So this is what a lot of work has done, and ourselves included, with an earlier version of LIO. And what this is saying is if the program terminates, then we preserve your confidentiality and integrity. But what we're also saying is that we're not really addressing this because it's a low bandwidth channel, it's not really a problem, and leaking 1 bit per run is not a big deal. But suppose we add threads, and we want to do this because we're in a modern web framework, and without threads we can't say service multiple requests at the same time. Once we do this, with discard being present in the language, what we do is we amplify the actual channel. So now the termination attack is no longer 1 bit per run, but instead you can leak 1 bit per thread. What's even worse is that you don't need multiple runs to see what the result was. You can leak information within the same program. And finally, with having discard in the language and having threads in the language, we're introducing a new attack called internal timing. So this attack doesn't even require you to not terminate, and instead it just uses the fact that you can potentially have a race to a shared public resource. So as an example, we can implement the previous isConspirator function using 2 threads. The first thread just serves as a baseline. So all it does is it sleeps for 100 milliseconds and then writes this public channel, let's say just the string y. The second thread, on the other hand, just has our discard block, and it's just doing the same thing. So it's reading Bob's messages, it's going to check if he's ever spoken to Julian, and then if that's the case, sleep for 500 milliseconds. Anything above 100 is completely fine. Outside of this discard block, it's then just going to write to the same channel, just the string ES. Now, if he's ever actually spoken to Julian, what you should be seeing on this public channel is the string yes. On the other hand, if the match didn't occur, then you never slept in the discard block, so you'll be writing ES first, then Y. So we've essentially encoded the bit that we want to leak in terms of the output sequence. And one thing that I want to note is that this example is actually saying that you should have delay in the language, but this is not the case. You really don't need to rely on a scheduler or anything like that. In paper, we have an example that we just use mVars actually. Here we have these few problems, but there's a more fundamental issue behind this. And the thing that if you look at the way discard works, it's essentially letting you execute something sensitive and then perform something public. So in order to address this issue, what we need to do is decouple the execution of the computation executed within discard. So and the way to do this is simply by spawning a new thread and executing this computation in a completely different environment. And finally, by doing this, what we want is to essentially, whenever you have discard, to always take the same amount of time. So with this kind of observation, the way we modified the original LIO is by removing discard from the language and adding lfork. Now what lfork does is the same thing as discard. It lets you execute more sensitive computation and continue on executing your public continuation by just spawning a new thread and working in that thread. Finally, if you actually want to look at this result, we do provide a primitive for that, and that's called lwait. So whatever lfork returns, which is kind of like a labeled future, is used by lwait to observe the result and or termination of this thread. But the important thing to note is that lwait first raises your label, and so if there's the thread never terminated, it doesn't actually matter because who you're leaking this information to is somebody in a higher context and all. So let's look back at the termination attack, but now replacing discard with lfork. And if we do this, then lfork will always take the same amount of time, so the time it takes to execute write to public channel will always be the same, so we're always going to see clean on the channel. In other words, you can't leak information by not terminating. So there will always be a thread looping if there's a match, but we won't see this observation. We can observe this in a public channel. And the same is true for the internal timing attack. We can no longer affect the output sequence on a public channel. So in the first thread, we're always going to sleep for 100 seconds. This was just the baseline. But the interesting one in the second thread, now all we're going to do is replace discard with lfork, and the amount of time it takes to write to this public channel is always going to be the same. So since the first one always sleeps, we're going to write ES first and then Y. So again, we can no longer encode the secret bit in a public channel. So we've implemented this in the most recent version of LIO, and we've actually been using it for roughly the past 6 months in a production system called Hails. So the framework I actually mentioned is real, and we have a deployed website, so this is actually being used. And since this is a PL conference, I guess I should talk about some of the formal aspects. So we've extended simply type lambda calculus with threads L-fork, L-wait, and some of the other primitives from the first version. And we've also added n-bars as kind of one thing that performs side effects to make the language more interesting. Finally, the theorem we proved was actually stronger than most other theorems for dynamic information flow control systems. It's termination-sensitive non-interference. So what this basically means is that you can preserve your confidentiality and integrity even if some of the threads don't actually terminate. So to sum up, we have closed termination, internal timing channel, but by no means all the channels. One other timing-related covert channel is the external timing. So for this channel, basically, you can encode a value like, let's say 0, and the amount of time you take to respond back to the browser. You can encode 1 by taking a little bit longer, 2 a little bit longer, and so forth. So you can encode this information and the response time. Unfortunately, we can't close this channel, but we actually managed to mitigate it and do so in a kind of pretty elegant way using monad transformers. And with that, I'll take any questions.